Hello everyone. Today I'm going to demonstrate modeling of a Spur Gear as well as a Helical Gear using Creo 3.0. I was searching for some good tutorials on YouTube with software like CATIA, NX, SolidWorks and things like that. But I could not get any satisfactory tutorial wherein I could produce an accurate gear. Hence, I thought of making a gear model on my own. To begin with, we will define some parameters which will define the shape and size of the gear. Initially, we need to create these many parameters which are the input values for the gear creation. The first one is a stub teeth. It's a SR no type, and if in case we are making a helical gear, then we need to define whether it is a right hand or a left hand. For that we need again an SR no type parameter. Z being the number of teeth parameter. M is the module. Here I am creating gears using metric system, so only modules will be used. Phi 1 is a parameter for normal pressure angle. Beta 1 is the helix angle. Tooth width is again a width of the gear teeth alone, and this K, it is not used directly in creating the model, but when we make a manufacturing drawing of a gear teeth, we need to specify something known as BTL, that is base tangent length, and that is measured across certain number of teeth. That number is denoted by K. Then X is the correction factor which can be used in creation of a gear teeth. The rest of the parameters what you see here are created as a result of some relations which we will see in a later on. We will see it later on. Okay. To begin with, we will draw a circle . And before that we will also examine the relationships what we are using. From here the gear relations are starting. The rest of the relations are not related to gear manufacture. Here this is a common model for both helical gear as well as the spur gear, so we need to have some kind of if statements for creating the spur and the helical gear. So you can note down these relations, and I will explain the meaning and the purpose of each and every line here. Basically, if you know, helical gear is nothing but a spur gear with transverse module, and they are stacked one next to each other with a twist. So although the gears are defined using normal module M, the modeling of helical gear is done using transverse module, and we can treat spur gear as a special case of helical gear where helix angle is 0. So if beta is 0, we will equate transverse module equal to the normal module, transverse pressure angle equal to the normal pressure angle, and twist equal to 0. This twist is a parameter defined by me. This is not any standard parameter as given in any gear handbook. I will explain the meaning of this twist later on. Okay. If beta is not equal to 0, that means if it is a helical gear, then we will have to do these calculations. These are the formulae taken from the standard gear calculation handbooks. Transverse pressure angle is tan inverse of tan of phi of by cos beta. Here beta is the helix angle. Then we need to calculate the lead of the helix, then the twist. This twist, we should not get confused between the twist angle and the helix angle. Helix angle remains the same for a particular helix angle, but the twist angle varies as per the gear thickness. That is proportional to the, basically it is the lead apportioned to the gear width. If the gear width is equal to lead of the helix gear, then the twist will be 360 degree. If the gear width is some fraction of the total lead, then this twist angle will be proportionately the fraction of 360 degree. Then we will calculate the PCD. Then BCD. BCD is the base circle diameter. This is the circle from which we are defining the involute. Then R is the base circle radius. Theta is some angle that is 90 degree. This is required for defining the involute curve. Basically, when we unwind a point around the circle, we should specify the angle by which we are doing this unwinding. Here I have arbitrarily taken 90 degree as the angle of unwinding. It could be 70 degree, it could be 60 degree, because we are only taking the initial small section of that involute curve. Just for the convenience, I have taken 90 degree. And I have converted this 90 degrees into radians here. Then if the teeth type is set as stub teeth, then these proportions are used. ACD is addendum circle diameter, DCD is dedendum circle diameter. If the stub teeth is set to no, then these relations will come into effect. Then we are calculating this addendum, dedendum. These are not exactly used for modeling the gear, but these are the parameters which are to be reported in any standard gear manufacturing drawing. Hence, these parameters are calculated. Okay. Then the clearance, 0.25 times the bottom BTCL is bottom clearance. Then profile shift is X times M. Okay, we will stop at this thing. Then we will go to the modeling. Then again we will come back to relation to see what these things mean to us. Okay. Now we will create a circle, and using relations we will set that diameter value to parameter ACD. Similarly, we will create two more circles, one corresponding to pitch circle. Later on we will change the line type to center type. Then a third circle corresponding to dedendum circle. Again, through relations within the sketching environment, we will set the diameter value to DCD parameter. Now this is the time for us to define the involute curve. This curve is defined with the help of a parametric equation which is shown here. You don't have to worry much about the correctness or how to derive this formula. Believe me, this is a correct formula for creating the involute curve. You can simply note down and use it in your modeling exercise. And you have to choose the default coordinate system, and the Cartesian type is to be selected. Okay. Now if you observe, the starting point of this involute curve is starting from the top plane, and the distance between the start point and the center of these circles, that corresponds to radius of the base circle. Okay, so although we have got the correct involute curve, this is not, we cannot create a symmetric teeth with respect to top plane with this. We need to shift this by some angle. For that we will have to create some datum features. So we will create 2 points, one at the center of the circle, the other one is the intersection point of the involute curve and the PCD. We will also create an axis as an intersection of right and top plane. Now we will create a datum plane which will pass through this axis as well as this plane, this point, sorry. You can see this datum plane 1 is passing through this datum point. Now we will create an angle measurement feature. And we will name it as ang offset. And we will also create a parameter called angle, which will define the angle between the top plane and the datum 1 plane. Now we will go back to the relations. Now the purpose of making these manipulations is to make the gear teeth, at least one gear teeth, symmetric with respect to the top plane. So for that we need to have an involute curve which can be mirrored across the top plane to create the top plane, the gear teeth. So for that we will see what this D14 means. 360 by Z gives total angle covered by one gear teeth and one gear gap. By 4, if we do that, we will give half of the gear width or half of the gap between two gear teeth. That minus that angle whatever we have measured with respect to top plane and the DTM1 plane. So we are subtracting 360 by Z by into 4 and this angle. Okay. Now what I have done is I have copied this original involute curve, and using paste special command I have also pasted with a rotation. That rotation angle is D14. This is defined by these relations. Sorry about this. and this dollar signifies that it can take negative values as well. Now the newly copied curve is, this can be mirrored across the top plane. Okay, now on the front plane I have created one sketch using the first copied curve and the mirrored curve, then something extra from the dedendum circle, just so that I am assured of removing material all through the thickness, and here the dedendum circle like this. And this is also the fillet, root fillet is also controlled using a relation like 0.3 times the module. Now we shall draw a sketch in the right plane. Basically it's a straight line. The length is corresponding to the tooth width. Maybe it is defined outside. Just a second. Yeah, D7 is tooth width. D17 is equal to tooth width. You can see the relationship here. Now we will create a variable section sweep. Just remember to make it surface. That last sketch what we draw as the primary trajectory. And a straight line up to pitch circle diameter, and we need to use the relationship 90 plus traj par into twist. Okay. Since at this point of time we are making a spur gear, twist angle will be 0, so we are getting one flat rectangular surface as a result of that variable section sweep. Now we will create one extruded solid. The sketch will be addendum circle, and the tooth thickness will be corresponding to the parameter tooth thickness. We will create the chamfer. Again they are controlled by the relation m/4. Okay. Now we'll have to create one single teeth. It is solid material removal, constant section. The profile is the sketch what we drew in the earlier, and the trajectory is the end surface, the edge of the surface of the previous variable section sweep feature, and it is constant normal direction with respect to front and normal surface. Okay. Then we will have to pattern it. Again the number of instances are controlled by the number of teeth, P46 equal to Z. Okay. Up to here the creation of a gear is complete. Next few datums are added. They are basically used for assembling these gear teeth in meshing condition. So we will create a datum plane DTM2 such that it will pass through the central axis, and also it will create some angle with respect to top plane. That angle is again controlled using a relationship. Okay. Here it will be very difficult for me to explain the every relations here, but basically what I am trying to do is I am creating a point which lies on top that DTM plane, which is almost diagonally or diametrically opposite to the first teeth gap what we created. If the number of teeth are even, then this will be slightly offset. Then if the number of teeth are odd, then it will be exactly diametrically opposite, which we can see now. So there is a small logic built into finding the number of teeth, whether they are even or odd. Basically this will determine whether the number of teeth is even or odd. If it is even, this is to be done. If it is odd, this is to be done. Then we have defined the relationship between these things. These are some of the relations which are used for again reporting the required parameters in the gear drawing. Also I have added an annotation like this. Since what we have modeled is a Spur Gear, it says Spur Gear. The moment we give some value for the beta, say for example if I change it to 25 degree and if I regenerate the model, the annotation gets automatically updated to helical gear. That is controlled using these relations. You can see the angle is 25 degree, which is exactly equal to the helix angle what we had given here.